Hi guys, welcome to the Dive Academy. And today I wanted to talk about best mixed gases. That could be Nitrox or Trimix. Stick around, it's gonna be cool. So why do we want to do a video session on this? And actually before I start this video session, I want to put in a little disclaimer. Although I'm going to show you how to calculate these mixes, always make sure that you dive according to your limits and also your certification, right? So although I'm going to break this down for you, that doesn't mean that you should dive to these depths if you're not certified to do so. Anyway, we have this out of the way, so let's just dive into it. So why do we want to know this? Well, quite often I bump into divers that have done their Nitrox course, or maybe they started some technical diving, and they tell me that their instructor said, oh, download this particular app because it's really good and it will tell you everything you need to know. Or yeah, I use this app because it's really good for planning. And the essentials of understanding what gases we can use safely at certain depths is very often either not explained properly or just completely skipped. So no agency bashing here or no pointing fingers to certain instructors. I personally think that this is really important information to know. So how do we calculate this? As you can see, I have my iPad here. This is one of my training tools I use, and I use a program called Notability. I'll open a new little note and we can dive straight into it. So let's see how long this is. Maybe I'll break this up in two parts and maybe it will be one long video, but let's look at Nitrox. Most people have a Nitrox certification, so we can start with that. In order to calculate the right gas for the depth, we need to know a couple of things, right? We now need to know the depth. This is in meters. Sorry, I'm a metric guy. And we obviously need to understand what the maximal partial pressure of oxygen is that we can breathe. So that's PPO2. If you remember from your Nitrox course, there's two numbers that we primarily focus on. One of them is 1.4, and then there's another one for 1.6. I don't want to talk about the deco part because 1.6 is for continuation and deco diving. But we're not going to mention this, but this works anything. You know, for the rebreather divers on there, 1.1 is something you might remember. So we're not going to talk about any of these. We're just going to focus on the bottom phase of the dive, which is 1.4. What is this 1.4? It's a partial pressure of oxygen that we can tolerate in our body, or we will tolerate. After that, we have obviously potential or an increased risk of CNS, oxygen toxicity, and we don't want to go there. So we know that 1.4 is the maximum partial pressure of oxygen. So it's kind of important, so I'm going to put a box around it, so we know that this number is what we're working with. Good. Now the depth in meters is obviously, can be anything. Can be 30 meters, can be 40 meters, can be 100 meters. It really doesn't matter. It really depends on what you want to do. So you need to obviously know where you're going. Now, how do we calculate the depth in meters to bar? There's a simple equation for that, right? Depth divided by 10 plus 1. So depth divided by 10 plus 1, where does this 1 come from? So I always try to I like to try to simplify things, but I also want people to understand where this is coming from, right? So if I draw the water column or cut out on the water, this is one of my favorite things to draw, and I'm still good in drawing. So we have obviously the surface of the water, and then we have our bottom. So here we would have 0 meters deep, and here, let's say, for example, we have 40 meters. Now we know that on the surface there's also pressure, there's 1 atmosphere. That atmosphere comes from the air. A lot of people believe air doesn't weigh anything, but air definitely weighs something. There's a lot of air above us, so that weighs down on us. We don't feel it, but it's there. I don't want to go into that right now, but we know that there's 1 bar of pressure. So this is the 1 bar that we also add here, because this part of the equation is figuring out the hydrostatic depth. And the hydrostatic depth, hydro is water, So that's that part, plus the 1 atmosphere from the surface will give you the total pressure or the absolute pressure, however you want to call it. So if we have here 1 bar, and we're obviously going down, we know that the pressure increases. Now the pressure increases because of the water column weighs a lot more than air. So for every 10 meters of seawater, we will get 1 atmosphere. So here it's 10 meters, and then there's 20, and there's 30. So we'll get something. So how does it work? Well, we could count them, sure. But there is a much easier way. Depth divided by 10 plus 1. Let's see if that works. So if I go to 40 meters, I divide that by 10, the outcome would be 4, which is the hydrostatic pressure, plus 1 from the surface would be 5. So that's how we calculate the depth. So far, I think straightforward, right? Why is this information important? As you remember from your Nitrox course, you learned how to use something which is called the Dalton formula, or the Dalton diamond, or the Dalton triangle. I like to call it the T formula, but it's basically because of Mr. Dalton figured out that we can make a total sum of all the pressures and look at the partial pressures. So the partial pressure together would make the total pressure. And it looks something like this. We take a T, and if you want to be really, really fancy, you could turn it into a diamond. Now, I don't really like that, so I removed it. So we're left with the T formula or the Dalton diamond without the fancy diamond stuff. So on the top, we write our partial pressures. Here we write our total pressure. And here we write our percentage of oxygen. Now the total pressure is equal to depth, right? Okay. And this here is a percentage. At school, we learned that we can't compare a banana and an apple. We need to obviously make sure that we always have the same measurements. So apples and apples, or in this particular case, pressures. So this is good, this is good, but this is not good. Now, let's have a quick look at air. Air is 21% O2 and 79% nitrogen, and this makes together 100%. There's another way of writing this. Remember, here we have 1 atmosphere, so we could write it as 0.00 bar or atmospheric pressure. 0.21 of that is oxygen, and if you then calculate that, you would have 0.70% nitrogen. So this is another way of writing that. Percentage means nothing more than percentile, right? Which is 1 percentile of 100 is 1, and 21% or percentile of 100 is 21. But this is another way of writing it. Now the cool thing is that this is bar or pressure. This is a unit. And this is also a pressure unit, which means this is also pressure unit. So the percentage can be converted to bar by just dividing this number by 100. So we know that this is percentile, but we basically need to divide that by 100 in order to get partial pressure, right? So let's have a look at that. I'll just put this as a reference in the corner, so here. And let's start figuring it out. Now, if you have this T formula, or the Dalton's triangle, whatever, and you know 2 things, you can figure out the third one. That's just really basic math, right? So what do we know? Well, we know the partial pressure. In this particular case, we want to know the partial pressure of oxygen, which is always going to be the bottom phase, 1.4. So let's write it down. 1.4. We also know the depth. We already calculated it for 40 meters, which is 5 bar. This formula works as follows. Everything that is above the line should be divided by what's under the line. And that will give us the answer of the unknown. So let's just open a calculator. If I take 1.4 and I will divide that by 5, I'll get an answer, which is 0.28. Now this 28 is oxygen, or in other words, 28%. So that's how we calculate the partial pressure of oxygen, or the percentage of oxygen we can maximum have for our desired depth. This also works the other direction. As you all know, most dive centers will offer you Nitrox 32. And they will tell you that the maximum depth for that is 30. But this is true. Let's have a look. We know that the maximum partial pressure for recreational diving on the bottom phase should be 1.4. So that's something that we know. 1.4. Now, we also know that most dive centers will give us 32% or 0.32. So now we know two pieces of information, and then we can calculate the depth because we have something on the top and something on the bottom. That means that we have to divide. So let's go back to my calculator. 1.4 divided by 0.32. So the answer is 4.375. Let me put this on my iPad. 4.375. And it is at this point that a lot of people get really confused. And they're like, well, hang on. Can we only dive to 4.375 meters? Sounds not great, right? So there must be a mistake here. Well, there's no mistake because remember, this is bar. So we need to now calculate back from bar to depth. If you see this equation, we can also go in a different direction. So if we want to go to depth, we can reverse this. So plus 1, so whatever the answer is, x, whatever, or the answer that I got here, right? Minus 1 multiplied, because that would cancel out this one, 10. Now let's try that. If the answer is 4.375 minus 1, so 4.375 minus 1 would be 3.375 multiplied by that by 10. So let's have a look at my calculator. So we take this number, minus 1, 3.375, multiply that by 10, and then the answer is 33.75 meters. So this is 33.75 meters. So when they tell you that the maximum depth is 30, technically that's incorrect, right? You can go to 33 meters. So I always try to round it down. You can't go to 34 meters because that would mean that the partial pressure will be higher. So out of safety and also because it's much easier, we say, you know what, don't go deeper than 30. For a lot of people, that's the maximum depth that should go to anyway, because that's what their certification allows them to for. But this is how you can calculate that. I hope that makes sense. So another way quickly to do that, if you would have your gas, let's say 32, and you say, you know what, I'm going to go to 30 meters, which is 4 bar, right? We can also calculate what the partial pressure is. And I just want to show you this because you can see how these are related to each other. I'm not trying to insult anyone's intelligence, but just show you that this can go in different directions. So if there's nothing above the line here, there's no dividing going on, so there's multiplication here. So if we do that, 0.32 times 4 would give us a partial pressure of 1.28 partial pressure of oxygen. So not 1.4, but perfectly fine within the limits because 1.28 is less than 1.4. So hopefully that helps with people that want to understand how to calculate this part for Nitrox. So if you're interested and want to have the aspiration to become a tech diver, I would suggest you just stick around. For the technical divers, you could jump directly to here, of course. So now we know how to calculate Nitrox. Let's have a look at Trimix, because it's not that much more complicated. So, same thing. The partial pressure of oxygen is always going to be 1.4, which is the maximum partial pressure of oxygen at our target depth. So if I know the target depth, I can start planning what gas I want. So let's assume that we're going to dive to 45 meters. So the depth is 45 meters. So that is obviously 5.5 atmospheric pressure. This one is important, so put a box around it. And this one is important, so put a box around it. So now we know that in Nitrox there is only two types of gases. There is the O2 and there is the nitrogen. Obviously, if we go to 45 meters, we can easily calculate what our maximum oxygen percentage will be. Or, the partial pressure is going to be 1.4. We want to understand what gas we have to put on our cylinder. So how do we calculate it? Well, same thing, right? Little T formula going on here. The maximum PPO2 is 1.4, and our maximum depth is going to be 5.5. 1.4 divided by 5.5 equals 0.25 something. We round it down. So here we go. 25%. If we know that the oxygen percentage is 25% and we just would dive nitrox, that would mean that if we want to make 100%, we would have 75% nitrogen in our gas. Now, 25% oxygen or 21% oxygen is not that much different, but we're not interested in the oxygen part right now. We're interested in the nitrogen part. If we would dive 75% nitrogen, it would not make that much difference. So other than that, we will be still probably very narcotic at certain depths. So we don't want that. So we want to reduce the amount of nitrogen. So the only way to do that is to put more oxygen in it, but that's not possible because that would mean that the partial pressure of oxygen would go up. So then we need to reduce the nitrogen by another way. We can introduce a third gas, and this gas needs to have a couple of characteristics. Preferably not narcotic. It should be lighter than nitrogen, and we want it to be as inert as it can be. Now, there's a couple of options on the periodic table, but if we want to take all these things that I just said in consideration, less dense or less heavy, and not narcotic, only two gases remained on the periodic table, which is hydrogen and helium. Now, hydrogen is the first element on the periodic table and the most abundant gas in the universe, but it's also extremely reactive, and it reacts really, really readily with oxygen and creates water with a big bang. We all heard the stories about the Hindenburg. So having a hydrogen in your tank together with oxygen is not a good idea. We do use it for diving. That's for very deep mixes with low percentage of oxygen. This is out of the scope of this session. So if we eliminate hydrogen, then the only gas that is available to us is helium. So helium is a light gas, doesn't have any narcotic effects at any normal depths. I say normal depths because if you go really deep with helium, it introduces a whole set of different problems. But again, this is out of the scope of this session. So for the depths that we're planning for, helium is a really good gas to introduce into our gas. And we all know this as Trimix, which is written as TMX, right? So Trimix. We know already that our Trimix mix is going to contain 25% of oxygen, but we don't know what the helium percentage is going to be. So how do we calculate it? Now you can pause this video and you can open your favorite decompression program or whatnot, or you can just stick around and we can calculate it without any of these fancy programs, because the answer is not that difficult. Before we start calculating, we need to know one more piece of information. We want to understand how we feel at a certain depth, and by doing so, we want to look at the equivalent narcotic depth. You might have heard about this before. Basically, what this is if we would dive on air to a certain depth, we would feel still perfectly fine, or this is where on the border where we start feeling narc. So if we know what that depth is, we can take that maximum partial pressure of nitrogen and add that to our little equation. So a lot of people take an equivalent narcotic depth of 30 meters, which would be 4 bar. Now, personally, I like to dive an equivalent narcotic depth of 24 meters, which is 3.4 bar. This is the total pressure of the gas at that depth. 24 meters will have 3.4 bar. Most trading agencies say that you can have a maximum narcotic depth equivalent to 30 meters. Now, I personally think this is a bad idea, because even if a lot of people will tell you, oh, I feel good, I feel fine. If your water temperature is cold, or if you are experiencing limited visibility or high task loading, or maybe you're in a teaching capacity, or you need to do something which you didn't plan for, there's other things we need to take into consideration. For example, CO2 retention, just general nervousness and whatnot that will make us feel more narcotic. So I personally choose to always dive with a lower narcotic depth, which is 24 meters. And depends on what depth I go, I might even lower that. So 24, I think, is a really good number. So we take that depth, 3.4, multiply that by the nitrogen that is in air, and this gives us an answer. Go back to my calculator. 3.4 times 0.79 is 2.686 partial pressure of nitrogen. Now, this looks important, so I'm going to put a box around it. We calculated the nitrogen. And you know what's really interesting? Remember, right? We have 5.5 minus 1.4 is 4.1 nitrogen plus helium, right? This gas plus this gas is this gas. So this here, we can break up. Well, look at this. We already calculated our nitrogen. So let's do this equation again. 5.5 minus 1.4 minus 2.686. 5.5 minus 1.4 is 4.1 minus 2.686 equals 1.414. This is your oxygen, this is your nitrogen, and then this is your helium. So funny enough that these ones are pretty close together. That is not related to anything, but this is what the equation is. It's simple math, right? Now, so if you take these numbers and you put them back into a Dalton triangle, let's see what happens. Instead of looking for the partial pressure of oxygen, I'm going to look for the partial pressure of helium. 1.414. What is the total depth? 5.5. And you know what? I can do the same thing for nitrogen. 2.686, 5.5. And the one from oxygen we already knew, 1.4, 5.5. So let's have a look. This one was 25 because we already calculated it, right? We calculated it here. Let's do the one for nitrogen. So 2.686 divided by 5.5 is 0.488, so we round it up to 49. And then the one for helium, 1.414 divided by 5.5 is 0.25 something. So let's call that 0.26 rounded. Now let's have a look. 0.25 plus 0.49 plus 0.26 is 1.00. Interesting, right? Basic math. Let's have a look at that. 0.25 plus 0.49 plus 0.26 equals 1. So we can now extract this information and put it in our Trimix. So here is the number that we were looking for. We'll have a look. We have here the gas that we need. We never write down the nitrogen, but I just wanted to show you how to calculate it. So our gas is going to be best mix based on an equivalent alcoholic depth of 24 meters, 25, 26. And that's our Trimix. I hope you guys enjoyed this calculation. If you have any questions about more types of gas calculations or maybe some gas density or gas blending, please send me a message or just write a comment below, and I'll see you in the next one. Thank you so much.